be strong.
Hey everyone, welcome to InDepth Academy. This is the first session of the series straight from the book. In this series, we'll read the NCERT textbook and parallelly go on understanding each and every line written in it. In this, we'll be covering mathematics, the first chapter, real numbers, the first part of real numbers, section 1.2, which involves the fundamental theorem of arithmetic. So let's get started. The fundamental theorem of arithmetic. That's the first thing that comes to mind when you talk about real numbers, which we actually have been learning since so many years, but not in the form of a theorem. So in this year, in grade 10, you're going to learn it in the form of a theorem. In your earlier classes, you have seen that any natural number can be written as a product of its prime numbers. Any natural number can be written as a product of its prime factors. For instance, 2 is equal to 2. Why can we write 2 is equal to 2 into 1? No, you cannot. Because when you say 2 into 1, 1 is neither prime nor composite. So 2 is equal to 2. That's how it must be written. 4 is equal to 2 into 2. 253 is equal to 11 into 23. Now how do you know? 253, this is the divisibility criteria for 11. It can be written as 0253. So the digits in the alternate places, they need to sum up to equals. So 0 and 5, they sum up to 5. And 2 and 3 sum up to 5 only. So 5 is equal to 5. Hence 253 is a multiple of 11. You divide 253 by 11 and you get 23. Since you know 11 and 23 are prime numbers, they become the prime factors of 253 and so on. Now let us try and look at natural numbers from the other direction. That is, can any natural number be obtained by multiplying prime numbers? See, now you are taking a natural number and you are saying it is a product of prime numbers. So can you do it the other way around? This is equal to, so anyways it's the same thing what we are trying to prove. So the question is, can you do it the other way around? Let us see. Take any collection of prime numbers, say 2, 3, 7, 11 and 23. You have taken 5 prime numbers. If we multiply some or all of these numbers, so you can take some numbers like 2 and 3, 3 and 7, 7 and 11. You can just take some of them, or 2, 3 and 7, or you can take all 5 of them, allowing them to repeat as many times as we wish. So I can say 2 into 3, 2 into 2 into 3, 2 into 3 into 3. So each number can repeat as many times as we wish. We can produce a large collection of positive integers. Actually speaking, you take, see in the bracket is mentioned, infinitely many. So if you take a single prime number, let's say 2. So you go on multiplying with it with itself infinite times. So it keeps on repeating as many times as we want. 2 into 2 into 2 into 2, it just goes on. So you get 2, 4, so you get 2, 4, 8, 16, it just goes on, right? So let us list a few. 7 into 11 into 23, which is 1771. This entire thing. So you're taking sum of these 5. 7, 11 and 23. You're taking 3 out of these 5 numbers, multiplying them with each other, and the product is 1771, which is a natural number. And 3, 7, 11, 23. So you know 7, 11, 23 is 1771. You're multiplying the entire thing with 3, which is another prime number from this list, and you get 5, 3, 1, 3. And in the next example, you are multiplying all 5 numbers. See, we mentioned. See, the first 2 cases are sum of these numbers. This third case is all of these numbers. Now the fifth case right below that is you are taking all of the numbers, but you are letting 2 repeat. 2 is used twice. So 2 into 2, 2 square. You are letting it repeat as many times as you wish. Okay. And another example for that, this is not very related to it, but still, it is an example. 2 into 2 into 2, 2 cube. So 2 into 2 into 2 into 3 into 7 into 7 into 7. So you are letting 7 repeat, you are letting 3 repeat. Now let us suppose your collection of primes includes all the possible primes. All possible primes. See, suppose I say collect all primes between 0 and 30. Then you know that there is a starting limit, there is a starting point and ending point. So there are limits on both sides. So, you can find the prime numbers in between 0 and 30. But if I say all possible primes, then it can go up to infinity. So there are infinitely many primes. So that's your collection. Your collection is of infinitely many primes. What is your guess about the size of this collection? A collection is basically you have infinite primes and you are multiplying it in all possible ways. So what do you think, what size? So you took 5 primes and you multiplied all possible ways. There are infinitely many ways. We just explained, we just saw. So there itself we have infinitely many numbers. So what is the size of this collection? It has infinitely many integers. Does it contain only a finite number of integers or infinitely many? Infinitely many. In fact, there are infinitely many primes. So there are infinitely many primes. So if we combine all these primes, see, this is what we spoke about, infinitely many primes, because there's no ending point, there's no end limit, right? All possible primes can go up to infinity, so you will get infinitely many primes. So if we combine all these primes in all possible ways, and we just discussed all possible ways means infinitely many ways, so infinitely many primes, infinitely many ways, put them together, then you will get an infinite collection of numbers, all the primes and all possible products of primes. What does this mean? Suppose we have 2, 3 and 5. Okay, so you can just leave them as they are. So 2 is not used, 3 is not used. Then if the other prime numbers are not used, you get these itself. You can also get 2 into 3 6, 5 into 3 15, and so on. You can keep on getting. So it involves all the primes. You have all the primes as they are and all possible products of primes. You get all the possible products of primes. That's what they're trying to convey. The question is, can we produce all the composite numbers this way? Yes, certainly. In fact, the very name composite has it. The very name composite suggests that it is composed of prime numbers. That's the reason it's called composite. What do you think? Yes, I think all composite numbers are produced this way. Do you think that there may be a composite number which is not a product of powers of primes? Certainly not. There cannot be. Before we answer this, let us factorize positive integers. That is, do the opposite of what we have done so far. What have we done so far? We have taken prime numbers. I know I am repeating this example so that it's in perspective for you. We have taken prime numbers, we multiplied them, and we've got a positive integer. Now what we're going to do, we're going to take a positive integer and we're going to factorize it. We're going to use the factor tree with which you all are familiar. In the previous classes, factor tree was taught, so we must be familiar with it. Let us take some large number, say 32760, and factorize it as shown. So 32760 as shown here in this factor tree. If you divide it by 2, you get 16380. Again by 2 you get 8190, again by 2 you get 4095, and 31365, 3455, 591, and 91 can its prime factors are 7 and 13. So this can be written as 2 into 2 into 2, which is 2 cube, into 3 into 3, 3 square, into 5, into 7, into 13. You will write it in this form if it has to be written in terms of the powers of the primes. In terms of the primes, then you will write entirely 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. But if you have to write in terms of powers of the primes, 2 cube into 3 square into 5 into 7 into 13. This is how you are going to write it. So we have factorized 32760 as 2 into 2 into 2 into 3 into 3. So this is what we discussed as a product of primes. So when you're writing it in terms of primes, it needs to be written entirely like this. However, if you're writing it in terms of products of powers of primes, then 2 cube into 3 square into 5 into 7 into 13. 2 cube is a power, right, of 2. So it's a power of prime. Let us try another number. Say 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 can be written as 3 square into 3803 into 3607. So 3803 and 3607 are primes. You will have to check that they are primes. So how do you check? Trial and error method. You keep dividing it by different prime numbers, and depending on what you get. So try it out for several other natural numbers yourself. This is kind of a test given to you, or an activity given to you. This leads us to a conjecture that every composite number can be written as a product of powers of primes. This is what we had discussed. Every composite number can be written as a product of powers of prime. In fact, this statement is true and is called Fundamental Theorem of Arithmetic. the fundamental theorem of arithmetic, because of its basic crucial importance to the study of integers. See, the study of integers cannot be done without this, because everything related to integers, at one point or the other, the root is surely going to be prime numbers. So the fundamental theorem of arithmetic establishes that every composite number is a product. It can be expressed as a product of powers of prime numbers. So hence it has its basic crucial importance in the study of integers. Okay, let us now formally state this theorem. See, until now we have, in an explanatory way we have understood it. Formally, the statement, the definition, every composite number can be expressed or factorized as a product of primes. This is very important. Composite number can be expressed as product of primes, and this factorization is unique. What do you mean by unique? If I say 2 into 3 is equal to 6, 2 into 3 is equal to 6 only. It can't be equal to 12 or 24, 48, anything else. It's just going to be 6. However, I can say 2 into 3 is equal to 6. I can also say 3 into 2 is equal to 6. So, apart from the order in which the prime factors occur, the order doesn't, the order can change. Apart from the order, everything else is unique. So that is one exception. And we'll speak about the order later in the same session. An equivalent version of theorem, not 1.2, it is 1.1, which is the fundamental theorem of arithmetic. An equivalent version of this was probably first recorded as proposition 14. Generally, they don't ask, but better safe than sorry, so you can be prepared. Proposition 14 of book 9 of Euclid's Elements. Euclid's Elements was the name of the book before it came to be known as Fundamental Theorem of Arithmetic. However, the first correct proof was given by Carl Friedrich Gauss in his Disquisitions Arithmeticae. I don't know whether I pronounced it right, but yeah, this is the name of the book. Carl Friedrich Gauss is often referred to as the prince of mathematicians and is considered one of the three greatest mathematicians of all time, along with Archimedes and Newton. He has made fundamental contributions to both mathematics and science. If you see all three of them, Archimedes also fundamental contributions to mathematics and science, Newton also, and Carl Friedrich Gauss also. Okay, mathematicians' names might be asked. Generally, again, this also they do not ask, but better be prepared. So Carl Friedrich Gauss was the person who gave the first correct proof of the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that every composite number can be factorized as a product of primes. Actually, it says more. It says that given any composite number, it can be factorized as a product of prime numbers in a unique way, except for the order in which the primes occur. We discussed this. There is one exception, the order. 2 into 3 is equal to 6. 3 into 2 is equal to 6. That is, given any composite number, there is one and only one way to write it as a product of primes. So given any composite number, 6 is a composite number, there is only one way to write. I can write 3 into 2, 2 into 3. Okay, order doesn't matter, but rest is unique. There is no other way in which I can write it. As long as we aren't particular about the order in which the primes occur. This is what we discussed. So for example, we regard 2 into 3 into 5 into 7 as the same as 3 into 5 into 7 into 2, or any other possible order in which these primes are written. Only the order changes. The fact is also stated in the following form. This fact. The prime factorization of a natural number is unique except for the order of its factors. Only the order changes. For this order, we need one solution, no? Because see, if it's 6, 2 and 3 are the only two factors, so we get away with it easily. But if it's any other big number which has, let's say, 20 to 30 prime factors, it could be there. So, you have 20 to 30 prime factors, and if you put it in all possible orders, just imagine the mess created. So we need some convention for this. So the convention is, in general, given a composite number x, let x is equal to 6. So given a composite number x, we factorize it as p1, p2 until pn. So p1 is, so p1 is this, p2 is this, and it just goes on. If you take any number, so pn, n is the number of total prime factors it has. So x is equal to p1 into p2, like that it just goes on until pn. n is the total number of prime factors. So all the prime factors are multiplied with each other to get x, which is the composite number, where p1, p2, pn are primes and written in ascending order. Now this is very important. The convention we have taken up is we write them in ascending order. 3 into 2 is correct, but it is not right according to the convention. It is 2 into 3 because ascending order 2 is it is lesser than 3 and 3 is greater than 2. So in ascending order it needs to be written. For example, 32760, before that, if we combine the same primes, we will get the powers of primes. See, before that it is shown p1 is lesser than or equal to p2, which is lesser than or equal to p3, and so on. So pn, the nth prime number, is the greatest. You're getting it, right? So in this case, 2 into 3, 3 is equal to pn. It is the last prime factor. So it is the greatest among the prime factors in that way. So if we combine the same primes, we will get powers of primes. If we combine the same primes, what does same primes mean? 12 is equal to 2 into 2 into 3. Now same primes, 2 and 2 are same primes. So you combine them, you get 2 square. So 2 square. This 2 square is a power of the prime 2. So if you combine the same primes, you get the powers of the primes. For example, 32760 is equal to 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. So 2 into 2 into 2 is 2 cube and 3 into 3, 3 square. 5, 7, 13 are written as they are, and this is in terms of powers of the primes. Okay. Once we have decided that the order will be ascending, then the way the number is factorized is unique. There was one exception. That one exception was cleared with the convention. Convention means anything which makes it convenient for us. So with this convention, we cleared that one exception also. So now it is entirely unique. 6 is equal to 2 into 3. 2 into 3 is equal to 6. Unique. Close. 2 into 3 can't be anything else. Like it can't be equal to anything else. And 6 can't be expressed in terms of any other prime factors. Okay. The fundamental theorem of arithmetic has many applications, both within mathematics and in other fields. So this is the use of fundamental theorem of arithmetic. The examples will be covered in the next video. Thank you so much for watching. I hope you had something to take away from this video. Thank you and have a good day.